morning, good afternoon, and good evening, everyone, and welcome today to our podcast about wafer-level testing, photonics. My name is Mark Sigura. I'm Global Account Manager, and I'm very happy that Nikta is today with me. She's an expert for photonics. So please, Nikta, introduce yourself and what drives you at PI.
Thank you, Mark. I am very happy to be here and to geek out on photonics. My name is Nikta Jalayer, and for those of you who don't know me, I am the Global Portfolio Director for everything photonics at PI.
Okay, when I see photonics everywhere in news, and it seems to be everywhere lately, why has it become such an important topic now?
It has been a while that the world is focusing on photonics, mainly fiber optics. They have been used for long distance, long haul communication. However, photonics for other aspects of communication and data centers, it hasn't been getting that much attention. Recently, given the AI growth, the generative AI, like agentic AI platforms, it has been a very, very hot topic. Why? Because electrical interconnects, copper interconnects, they are running out of steam. So copper is no longer the answer to many of these applications, given the bandwidth you need, given the distances that you want to send data, and the energy consumptions, the energy requirements of each data center. You need to come up with a new technology. And that's where photons, instead of electrons, they can help and facilitate that transition.
Okay, so speaking about the heat and the power consumption data centers, and photonics is the solution you mentioned. So why isn't it deployed in every data center today?
So the technology is mature. Deployment is a different topic, though.
Okay.
When you are talking about deploying photonics integrated circuits in high volume, it means that you have to manufacture it in high volume, essentially. And there are some challenges around high volume manufacturing of photonics integrated circuits. So essentially, any technology that you want to bring to the world, it's very different when you think about technological advancement and maturity versus deployment in industry and the most important customers or accounts that they are working in that industry.
So I guess as many markets, we are speaking always about the challenges. Even when something is new, there are right in the beginning, every time, everywhere, some challenges. Let's dive a little bit deeper into those challenges. So what are the most significant hurdles the industry is currently facing?
So there are several challenges around manufacturing photonics integrated circuits in high volume. One is testing of optical components or optical devices is very different than electrical components. So for the historical, state-of-the-art IC test, you're dealing with tens of microns of pads or probes. That makes it, it is very, very precise still, yet it is much easier than photonics components testing. What do I mean? Photonics tests, it requires light to be shined from the input and then to be collected on the output. It's not the same as electrical probing. Electrical probing is just a touch. You come in contact, the connection is, exactly, yay, nay. If you were thinking photonics testing, though, you have to shine the light from the inputs and you have to collect a certain amount of power or voltage on the outputs. What does it mean? It means that you need very stable test equipment. On the other side, the features we are dealing with, they are orders of magnitude, if not more precise than IC tests. So let's say the paths, electrical paths, they are 50 micron in
Okay.
size, which is very small. Yet in photonic tests, we are thinking about 5 to 9 micron
Whoa.
field diameter. So it is much more accurate, much more precise comparatively. It is very, very difficult to test these components, and it is
sounds
more
very difficult.
time consuming. Yeah, absolutely.
Wow. So testing seems to be a recurring theme. And where in the manufacturing process should these optical devices be tested?
Previously, the photonics devices, they haven't been deployed in many parts of a data center infrastructure. They haven't been tested in many parts of the manufacturing process. So they only were tested after they are packaged. So on only package level or die level tests. However, packaging on its own, it is a very, very expensive process. We don't want a bad die from the very beginning to pass through the multiple levels of manufacturing process. We want to make sure that we catch the bad dies in the beginning of the process. And that means you have to run tests at wafer level. Wafer level tests, they might take longer because there are many dies that you have to taste. However, it helps your yield. It helps essentially the cost associated with manufacturing of these devices. So now the industry leaders, they think tests should happen in 4 different insertion points at a minimum. 2 on wafer level, and 2 on device or die levels. And wafer level, the more you shift tests to the left side of the processing chain, you get better yield, you get lower cost. That's the idea behind it.
So this whole story brings me to a very important topic and a very interesting question. So how does PI help to address these manufacturing and testing challenges? So what is our part in all of this?
So PI has been in the industry of precision motion and positioning technology for over 56 years. We know how to move things very, very accurately.
Good point.
We have been thinking about photonics devices and the integration of photonics devices for over 16 years. Again, before photonics, before photonics becomes something very important in the data center communication world. Knowing that, we can move things very precisely. Photonics integrated circuits, they require nanometer level stability of motion systems. And PI, with different motor encoder technologies that we provide, we are, I believe, in the leading position to offer the best systems that are good for testing of these devices. That and the algorithms that PI develops, we make sure that we are developing algorithms that are intended for production lines, and they reduce noises and temperature changes, and they are easy to use. So all of that is very much focused to help our customers meet their needs.
And I guess the customers' needs and the customers are really caring about is business outcomes, right? So,
absolutely.
And how do they benefit from these solutions?
Essentially, we are all about higher throughput and better yield to our customers, not us, essentially. Higher throughput and better yield means that you enable customers to provide multi-site testing. So you are testing a wafer on different positions. The latest development at PI, the Nova probe or piezo-based aligner engines, they are intended to focus on parallel testing and integration of those into the probe cards,
And
electrical
saving time,
probe cards,
yeah.
exactly, to save time, to save cost. And when you come in contact with a probe card, electrical probe
Yeah.
card, you're running optical alignment at the same time, and that means faster, higher throughput. What does yield mean? Yield means that you don't necessarily have to have different designs for different chip designs or PIC designs. In this case, photonic integrated circuits, they have like really insane number of designs. If PI can manage to offer the most accurate metrology system, let's say, for these solutions to be able to figure out where the trenches are, how deep the trenches are, integrating that without affecting a lot of the hardware design, that means that we did a very good job and we can standardize on different designs of PICs. And for that reason, we brought in our PI range result sensors.
Okay.
And we integrate those into the fiber array units.
Okay, what are these sensors?
So essentially, they can measure distances to nanometer level precision, meaning that you are dealing with a new design.
Okay.
You don't know what the design is. As a motion expert, you don't know what the photonic integrated circuit design is. You are looking at your distance measurement sensor, which is integrated in the fiber array unit. Okay. It is not adding much to the form factor and to the topology of your hardware, yet you can figure out where the trenches are, where you don't have trenches, where you have to run edge coupling, where you can use surface coupling, things of that sort. Essentially, you avoid collision. You make sure that your alignment is not designed for that particular design of PIC. It is more standardized to every design, essentially.
Okay, wow, very insightful. And I come to my last question. So, as a wrap up, where do you see the future of photonics?
I think it is going to revolutionize the data center and how data centers, they deal with data. Photonics, I mean, is going to revolutionize that world. However, we have to overcome these challenges, and that's why we are working with a good level of partners to make sure that we have enough understanding about the needs of the market to help and address those needs and requirements. But it is going to be a very interesting roller coastery ride. Buckle up.
That's a good picture. So I learned that we learn a lot from our customers in growing markets and upcoming new trends, new developments and new technologies. So we are very happy to work with our customers and learning from each other, that we can bring our knowledge about motion systems, sensoring, and all the stuff you explained as a solution. So we are always very happy to get into new projects with our customers together, to learn from your application, from your challenges. We heard some of them, but I think, and you said it already, it's a roller coaster. It's not the end of the line. And I'm very happy to learn a lot about photonics today from you, Nikta, and we are very happy and invite you to challenge us with your application and your requirements out there. So please feel free to contact us and give us a call, and thanks for listening. Thanks, Nikta, for being here.
Thank you. Thanks so much.